Good afternoon, everyone.
Good afternoon, ladies and gentlemen, and welcome to the third webinar in the MPMA PLASTECH MONTH 2021 webinar series. And today's webinar is entitled Design Rules for Optimizing Injection Molded Plastic Parts. We have with us an honored guest who also is the moderator for this afternoon's webinar. I will be introducing our honored guest a little later. To begin with, let me run through the etiquette or rules of the webinar. You would have noticed that we have muted and turned off video for all participants. This is because we are using a conference platform on Zoom, and this feature is activated to ensure no disruptions to the speakers during the webinar. Participants may ask or pose questions related to the presentations in the chat box during the webinar. The speakers will only answer questions that are clearly written and based on the presentations. Kindly refrain from marketing your goods or services in the chat box. Kindly also refrain from posting comments or remarks to questions posted in the chat box. The chat box is only for queries related to the presentations. The organizer reserves the right to remove participants who run afoul of the webinar etiquette. The MPMA PLASTECH Month 2021 is brought to you by MPMA with the generous support of sponsors from the Malaysian plastics industry. Please allow me to thank each and every one of them. Platinum sponsor, Monitor ERP System. Gold sponsors, PT Bobs Jakarta, Milliken Asia Pte Limited, NGR Malaysia Sendirian Berhad, Petronas Chemicals Group Berhad, Reifenhauser Blown Film GmbH, and Windmoller and Holshire Asia Pacific Company Limited. Silver sponsors, Arbeck Sendirian Berhad, Nord Mechanica SPA, and Cispro Software Malaysia Sendirian Berhad. Bronze sponsors, Autodesk Malaysia, Ben Mayer Specialties Malaysia PLT, Bruch Private Limited, Husky Injection Molding Systems Malaysia Sendirian Berhad, Recommend Malaysia Sendirian Berhad, Sigma Soft Sendirian Berhad, and Torre Plastics Malaysia Sendirian Berhad. Other sponsors, Kreiberg TPE Technology Malaysia Sendirian Berhad. Thank you to all our sponsors for making the MPMA PLASTECH Month 2021 a reality. In appreciation to our platinum sponsor, Monitor ERP System, for their contribution towards the event, we will now play Monitor ERP's corporate video. Thank you, Mr. Daniel Harkmark, the Managing Director of Monitor ERP System, for your support towards MPMA PLASTECH. Ladies and gentlemen, without further ado, let me introduce to you our honored guest and moderator. He has been in the plastics industry for 43 years and is currently the Managing Director of Plasform Sendirian Berhad. Plasform is engaged mainly in manufacturing parts and components and offers tailored plastic engineering solutions to customers in the E&E industrial, automotive, and special application sectors. He is MPMA's Secretary General, Chairman of MPMA's Human Resource Development Committee, and Chairman of MPMA's first ever virtual plastics conference, the MPMA PLASTECH Month 2021. It gives me great pleasure to present our moderator, Mr. Eddie Fong.
Thanks, Francis, for the kind introduction. Welcome, everyone, to our PLASTECH Month 2021. This is the third webinar today on the 11th. We're going to have another 6 more, actually, altogether 9 of them. So today we will have 3 presentations. Because injection molding and so on is such a vast topic, we can only choose a few, otherwise we'll take over the whole conference. The thing is going to run like this. The first speaker will be our Sachin Fulsundasan, or Mr. Sundar, Mr. Sachin Fulsundar. Let me get it right. Second one is Miss Lin Wei Yen. So after the talk from Miss Lin, we will ask for questions, for her to answer, because she has to catch a flight. So the other speakers will have to wait until the end of all the presentation to answer any of your questions. But Ms. Lin will answer your questions straight after her talk. So if you have any questions concerning what she is going to say, or something is not clear, you ask it during her time when she is speaking. Please post it on the chat box. We will get to it. And then last but not least, Mr. Yasunobu Sato, or Dr. rather, Nobuyasu Sato will be speaking on the engineering plastics. So let me give you a slight overview of injection molding. I think injection molding is a multi-discipline kind of a topic. First of all, you have to know how to design plastic parts. Make sure that you design it with the right shape, the strength, and so on, the statics, and so on. Secondly, you have to know your plastics material to know what sort of environment it operates under, whether it's high heat or acidic, alkali, high stress, low stress, and so on. So you have to know the strength and performance of these plastics material. Number three, you have to know about molds. Molds are an integral part of injection molding. And within molds itself, you have metals, that you employ to make your molds from. And steels, there are probably more than 24 types of steel that you can employ to make plastic molds. Then you've got to put other inserts of metal, beryllium, copper, etc., for heat conduction and so on. So that metallurgy itself is part of injection molding. Then you talk about machine types: electric, fully electric, hybrid, hydraulic, and so on and so on. So you have to know the performance of each type of machine, whether these machines are suitable for your type of operation. And the other thing you need to understand is ancillary equipments like robots, dryers, conveyors, material handling equipment, and so on. So injection molding is a very complex subject. It's multidisciplinary. Today, we're only touching on three aspects: designing, and then the prototyping, which is the verifying of your design, and so on. And then we look at some high performance engineering materials. So let me introduce our speakers for today. The first one is Mr. Sachin Fulsundar. He is a technical solutions manager specializing in Autodesk simulation portfolio. He involves himself in product development, processing, mold design, as well as simulation and CAD. At Autodesk, he worked with various manufacturing solutions, including Fusion 360, and has been involved with Autodesk mold flow products for the last 20 over years. That's our speaker number one. Speaker number two, Ms. Lin Wei Yen, brings 14 years of experience into the additive manufacturing arena. She joined ARBEC in January of 2015 until the present, and is the manager for additive manufacturing, handling all requests with regards to Freeformers. That's the brand of their 3D printer, if you like, and in the APEC region. Formerly, she has been a service engineer in the medical and industrial laser industry in the ASEAN region. Our final speaker for this afternoon is Dr. Yasunobu Sato. He is the marketing manager of the transportation sector for Solvay Specialty Polymers in Japan. Prior to this, he was the sales development manager, and before that, research scientist stroke engineer. He obtained his doctorate from Keio University in 2004 under Professor Haruma Kawaguchi. I was going to say Kawasaki, no, it's Kawaguchi. So we have very able and learned speakers to speak to us today. So let me then pass on the mic to Francis to introduce, get on to the first speaker. Thank you, Francis.
Dr. Sachin, I think you can proceed, Dr. Sachin. Mr. Sachin, sorry, I think you can proceed.
Thank you. Thank you for this opportunity. Let me share my screen. Let me know once you are able to see the screen. I hope you are able to see my screen.
Yes, we can.
Okay, thank you. Thank you very much. And first of all, thank you for the opportunity to be a part of this, privilege forum. Thank you to the Plastic Association and the board members, Mr. Ed and Francis and Sujata, so been kind enough to give us this opportunity. And as Mr. Eddie mentioned that injection molding is not in like a simplistic way, though it looks like, and he has well set already the forum to get started with it. Injection molding is just not like a replicating of the articles, but the process starts from a very minute detail of the concept design to the product aspects of it, and then replicating those CAD models into the mold, and then going into the details of the cooling, and finally the production comes out. In my today's 30 minutes of this presentation, I'm going to cover and touch base on each and every aspects of the injection molding. But differently, we are trying to see how this virtually can be replicated. As we are virtually now connected over here, I'm trying to touch base every aspects of the injection molding virtually and validating it before we go for the actual reality of actual implementations. And as Mr. Eddie mentioned, is that plastic materials are becoming more expensive, so we cannot really afford to have a test trials on it and see how these can be virtually be simulated. With that, I'd like to show you the glimpse of the agenda, what I'm going to cover for next like 25 minutes or so. I want to take this opportunity to introduce Autodesk Make Solutions. Trust me, I'll not take more than a minute to introduce it. And then we will jump on to the injection molding and see that what variables are impacting to this process. And we'll also touch base upon the product design part of it. And when you're talking about the product design, something that is already been started in the market is upfront decision making rather than working on a troubleshooting, and how we can take upfront these decisions and go with the confidence. We're also going to touch upon the mold cooling simulation part of it. I know that there's a lot of things are happening in the mold cooling. Everybody wants to create faster components, meet to the volume requirement, and there is a lot of changes are happening in the cooling. We are going to touch upon the basics as well as the upcoming technologies as well. And the last, probably, I want to show some of the glimpse of the upcoming technologies and advancement happening into the injection molding. With that, I want to introduce you to the Autodesk Make solution or product portfolio. As you see on the screen, Autodesk is been known as the company into the different segments. Probably you heard about the Autodesk into the architecture, engineering, constructions, media, but equally has a footprint into the manufacturing as well. And in manufacturing, we are having a broadest portfolio, right from the product design, engineering, production engineering, and distributions to the collaborations with the different segments or could be vendors, and using them on repeatability. Data management is becoming one important part of when we are working with the different teams in collaborations on it. But my team, or particularly my division, particularly focus on those highlighted areas where we work on to the generative design. Probably you have heard this word, a buzzword of generative design. This is something a design exploration. We give the constraints, and the artificial intelligence of the computer gives you the various designs, and you have choose upon. Once you select those designs, can be validated using simulations. And when you are trusted on those validation results, you can move on to the machining. Down there is a way of like machining is a subtractive operations or additive operations. And finally, we move on to the tool and die part of it. So today I would be a little bit revolving around these aspects as well as we go through the presentations, but without losing the essence of the today's topic, how well we can design the injection molds or the injection plastic parts also. Few of the common areas already working with customers, lightweighting, as you can see on the left-hand side of your screen, very, complex part. This is an heat exchangers, but today we could be able to manufacture it with the help of additive technology, and so as we can make it more lightweighted. This technology was of dream if you consider like an 30 years back or so. Of course, on the generative part, as you can see that we can do a lot of consolidations of the part, particularly the part that you see is a combination of the 8 part consolidated into the 1, and then we are using additive to manufacturers. We're also going to discuss onto the, we are helping into our customers onto the molded plastics and composites also on the validation part. There are performance tests needed onto the plastic or the metal part, how it's going to perform into the real life. We can pressure test as it into the actual real environment and see that performance. It's not only checking the performance for the structural point of view, but also checking the performance from the ventilations or the heat exchangers point of view. Last but not least is the something manufacturing. Now, manufacturing is in all the different way, but if you're thinking of tool and die, I would say that subtractive operations are mainly being used over here. So we help our customers in milling, turning, or CNC robotics and inspection part of it. And with that, I like to introduce the injection molding. And with the introduction, I want to also discuss upon some of the challenges. Now, injection molding process is it's been commercialized more than, I would say, 6 decades or more on so. And it's a complex process. The reason is that it's a combination of the time, temperature, and pressure. And if any of these variables are being disturbed, it directly impacts the quality of the part. Now, quality aspects are altogether different for each of the customer. Some of the designers would be worried onto the aesthetics, some are into the dimensional stability of the part. We'll discuss onto the latter part of the presentations. But it is estimated that 80% of the plastic part that's produced are injection molded. And so as this is one of the most popular injection molding or replication of the part technology available in the world. What we design, this is what we see on your screen. But when you not been upfrontly validating your part, or probably you want to directly mold this part as it is, I would say that, we land up creating these type of parts. And probably the people who are already formed an injection molding, they've experienced this type. It's happening and it's not new. And today we are going to touch upon some of the aspects, how to get the part that you desire into the actual reality as well. As we speak on the injection molding process, it's not a single process that you care is done and then you start for the productions. As you can see that it's a multi-staged process. It starts with a concept, part design, mold building, and productions. And of course, each of these steps has some objectives. As I try to see that, I'm not going to go through each and every of this, but like concept design, it has a shape and functions. But actually the risk associated with each of the steps is on the manufacturability. So each and every step, we need to check that whatever been added to the part or the details are getting added to your mold or the mold design process, are they manufacturable or not, or what things can probably go wrong. And if you're coming from a production or from the tooling background, what happens when the things go wrong. It's something that everybody wants to put that responsibility or the blame game to the others' shoulders. And this is not new. It's been there in the industry for a long time. And probably when we try to do this type of finger pointing, we lose a lot of money as well as the time on this. And probably we have to work on to the troubleshooting part of it. Now let's look at what are the variables that really impacting the product designs. We'll touch upon some of the variables and its categories. There are a lot to consider, but I try to jot it down into the three categories: part design, mold design, and processing. This is particularly like an egg and chicken situation, which one to address first actually. But and these variables also interact with each other, like the part design has an impact onto the mold design, and so as the mold design has an impact on the processing, and so as the processing the part design has an impact onto the processing part of it. Let's have a little deep dive onto each of these categories or variable categories on this, starting with the part design. Now, when you are designing a part, particularly example of an engineering, what they not only start with the geometry, but they also look upon the material as well. And when we think about the material in the world of plastics, it's not the single material. We have thousands of material, or probably more than that materials to choose upon. And if I need to categorize those, I would say that crystalline, amorphous, and fiber. And each of these has unique characteristics of it. Touching upon the product design, if you can see on your screen, I can design the product into the different way. But what is the smartest way is to avoid the chunkiness into the part. Okay, plastic is something that it really doesn't help as you increase the thickness, but it definitely helps into distorting the part. As you can see on the middle part, if I need the thickness higher, it's going to contract actually. The thermal contraction is happening. What's the best thing is to follow the plastic design guidelines and using a smarter way to design on this. A flat plate coming out of the mold really is not a flat, probably it needs some strength. So there is various ways to strengthen it. Could be adding of bricks or could be adding of one of ways corrugations to it. And the last is not the least, but I call the gate design is not the responsibility of the mold maker. Usually it say that, but I would say it's the responsibility of the engineering team, because a lot of things are driven by it. For an example, I can take a single strip and try to get it into the different ways, and each of it has an unique characteristics of the behavior. Probably the engineering team is the one who knows that what dimensions they need and how they can reach closer to it. Avoid making the blunders, like just having a number of gates will help to improve the quality of the part. On the variable coming on to the mold design, I talked a bit onto the gate locations and runner. These are directly impacting on your cycle time, particularly runner fit system. We need not to cool it 100%, but at least 80 to 70% they should be cooled before they are ejected out. Runners also impacts on to the cost of the part. Okay, I've seen that many of the time the parts are small and your feed system, but there is a necessity for it. But we can use techniques to optimize this runner or system. Cooling, we will discuss on it, but there is a lot of smarter ways to work upon the cooling, even you are going with the traditional cooling ways of it. And last not the least is the ejection systems. This is an example of an ejection, the part getting distorted, not because of the product design or the processing, but because of the ejection system that has been implemented. And you can see that the part getting snapped out completely of the mold, and look at what would be the scenario on the distorted shape of the part actually. And the last one is probably, before we jump onto the other aspects of it, is the processing. It's one of the complex way, and I have seen that many machines, they are running for like months with the same process settings because they don't really want to touch upon it. And why they don't want to touch upon it? Because it has a direct impact onto the quality of the part. Like I'm trying to highlight, like shrinkage has a direct impact onto the holding time, holding pressure, mold temperature, wall thickness, and the injection rate. Probably assuming that wall thickness is constant, but we can see that at least like a 5 of these processing variables has direct impact onto the tolerance of the part as well. Okay, and of course, the one that also impacts is the advanced processing. If some of the things cannot be manufactured using a traditional way, people try to do it in other way. Like for example, is a microcellular or the gas assist is the advanced processing techniques to meet that dimensions. Now we are talking about all these, causes. I'm not trying to, say that it's a complex process, but if it can be validated upfront, it can be a much easier way. With that, I like to introduce on mold flow. What this technology is all about. It's technology to process or the simulate injection molding and compression molding. Best part of that, it has a library of more than 10,000 materials to choose upon. You directly work upon the native CAD geometry rather than working on a IGS file or a neutral file format, any other. It has 12 molding processes to simulate upon that, and you can work upon the design of experiments to find the root cause of what's probably causing that warpage in the part or the seam marks in your part also. Results can be also be exported to the third-party solutions, particularly if they want to do the post molding operations part. Starting with the basic way, how the simulations can help you designers and engineers. When you are designing a part, unnoticedly, there would be chances that wall thickness may go up, and it can directly go for the, for the mold making. So simulations can help you some of the checks very instantly, like the wall thickness, draft angles, undercuts, and gate locations. As I told you, that gate locations is also important part of the engineering. We can also work upon the cost advisor, because this is something is needed by the engineering team if to support the RFQs. If you're getting an RFQs from the customer, you have to respond in that time. So, quick analysis can help you to get to the accurate material cost or the part cost. If you want to do a very detailed analysis, we do have other solutions for mold flow insight, which can help you to do the design of experiments or advanced processing like rapid heating and cooling, wall gating systems, shrinkage and warpage predictions, or what is the shrinkage exactly with precise dimensions can be very much, or advanced molding like the inset molding or multi-shot moldings can be performed with it. Getting back to onto the upfront decision matters. Why upfront solutions are getting importance nowadays rather than working on the troubleshooting? One of the things is to and probably I'm not going to spend a lot of time on to the troubleshooting. So if you look at it, why part design level simulation is gaining importance is that we are virtually testing the part before up in the production, or the mold design sense can be very costly and time consuming. So to avoid those time as well as the money, we can address these issues upfront using. So what are these things that can be addressed upfront? Some of the things that I already talked about is checking all your draft angles, undercuts, geometry thickness. It look upon the gating locations, number of gates, and potential weld lines, seam marks, and also look at the deflections and the shrinkage on this one. As you can see on the screen, the technology has been gone long way. You can really look at the part, how it is going to, virtually look at your part, how it is going to look like after manufacturing. So we really don't need to wait for even a prototypes to address potential issues. These can be virtually be simulated and corrective actions can be taken on it. We always talk about the simulations, how good results the simulation produce. I would say that simulation is something, if it is not going to produce the results as accurate as possible, probably you would be wasting that time on this one. So trusting on a good simulation software is much needed because you are completely relying on it, whatever the future decisions that you are going to make it on your costly molds. One of the examples that I want to show it before we move on to the details of the, of the cooling aspect of it. The like in the 30 years back, probably these type of cooling channels were designed. Actually, if you take an example of this part, this was like a simplistic type of cooling channels were designed. Later on, we developed the simulation capabilities and so on, and then we try to add baffles and bubblers to increase the velocity, to increase the turbulence in that area, and extract the heat from the deeper core areas. But today, the technology is altogether changed. We are thinking of having a much complex, closer cooling channels to the part so they can extract the heat much faster on it. So with that, I'd like to introduce the mold simulation capabilities that are available in today's simulation or the design aspects of it. So let's start with a very basic part of it, is the cooling line placement. Now, these technology has been there, I would say, right from the beginning, like in 6 decades or 4 or plus, where we've been using this traditional way of cooling. Now, what these comprise of? It's a single like a drill that straightforward lines goes and comes out on this. A little bit of now they started adding baffles and bubblers, and eventually we come up with the more guidelines. In the plastic, I would say there is no rules. We always say there is a thumb rules because these are the guidelines. They're not necessary every time they follows. And the simplistic change into your designs can improve a lot. Like an example over here is a simple part that has been designed with a traditional cooling, but if you're placing it rightly, probably you can extract the heat much. And this is where the simulation can provide insights. What's happening within your tool. Let me give another example of this is an cover of an drill machine which was designed with a very simplistic cooling, but with that we missed to cover some of the critical areas to cool on this. Now the result would be that probably the increase in the cycle time as well as the sink marks may appear on the other screen. What could be the best solutions to go with it is addition of the little bit of baffles, and the complicated area where baffles cannot really work on it, I may add the beryllium copper inserts. So these are the very simple things, or probably if you get an insight of that with the help of simulations, you can take in much corrective actions. And I call this as an upfront simulations rather than working on it troubleshooting. Now, as the technology goes into more advancement, probably you already heard about the word called conformer cooling. So conformer cooling is something, the cooling channels that are designed around your part. And probably conformer cooling, though it looks complex, it's expensive for the manufacturing part of it, but it has its own importance of it. That's the reason I thought of showing you a slide onto the conformer cooling versus the conventional cooling. The part that I showed it earlier has a deeper core. And if you look at the conventional cooling results, particularly on this part, I cannot able to cool on to these core aspects of it. They are still at very high temperature. Whereas the conformer cooling, this goes all the way inside the chip and I can extract the heat rapidly from it. What's the result of it? I'm increasing my productivity almost by 67%. I'm able to almost double down my productions also, and also I'm getting a reduction into my cycle time. The most another important part is improvement into quality. If your part is prone to sink mark or warpage because of the cooling, conformer cooling can be an a best solutions to look for it. With that, I want to introduce you to some of the advanced techniques that's going into the market. Particularly, now the people or the I would say the customers are becoming more demanding. They want to have a closest means closest quality component, as close as to the, I would say, CAD, what they see on the computer, the same way they want to produce the component, particularly in appliances industry and also into the automobile industry. The glossiness or the aesthetics has improved, the requirement has improved a lot. And one of the technology that is helping on is rapid heating and cooling. I can show you the example of the conventional molding versus the rapid heating and cooling, where you can hide the, some of the aesthetic defects like the weld line, which can be easily be hidden, as well as you can improve the glossiness of the part. Rocktool is one of the company that we've been working on it to help to produce these type of parts. Probably this uses the induction heating rather than using a conventional steam or the heated waters to it, because that has a lot of energy losses. I would say the induction coil is more effective. It can just heat the areas which are needed to be heated, and it rapidly cools down and you get the required part of it. The another technology is that's coming up. I just showed you some of the example onto the conformer cooling, but now customers are becoming more demanding. They are asking, hey, instead of like the conformer cooling, which we need to design, and probably we may not be the right people to design the conformer cooling, is there any technology that can help us in designing these conformer cooling channels? Because your part geometries are becoming complicated as we try to integrate more things into the single part. Can the artificial intelligence can help us over here? So Autodesk consulting team and Panasonic has worked on to the one of the internal project for the fan impeller. As you can see on your screen, it's quite a complex part in terms of the geometry. It has like a 5-dimensional type of geometry, and we use our upcoming technology or the consulting technology to design the conformer cooling. And this is one of the way of using a generative design. Generative design, particularly people are using it for the designing of the parts. So same way, generative designs can be used for the generation of the cooling channels as well. And as you can see that you can give the starting shape of the mold block, the part, and based upon the thermal loads and the boundary conditions that you have been assigning, the computer can come up with the cooling channels. Now these cooling channels can be of different shapes, like the cooling channel that you see on the left hand side of your screen is based upon the constraints that I don't want the cooling channels anything between around the part or just closer to the part. And the right side is without the constraint. And you can see that these cooling channels, they look a little bit very weird on shape, but these are very effective. Can these be manufactured using the traditional technology or traditional just the drilling way? No, it's not possible. Probably I can think of having a traditional technology or the traditional way of cooling with the cooling channels onto the left hand side, but onto the right hand side, definitely I have to go with the combination of the additive process or additive metal process. I create the inserts, and then probably I can use a subtractive operations for the rest of the thing. So this is called as an hybrid type of manufacturing. Many people, they are looking at, instead of making a complete inserts of the metal additive, some portion they are making of the metal additive and adding it to the subtractive part of it. So this was an example, and now the question arises, is this been implemented? Yes. So we got in some of the pictures from the customer where they have implemented the the cooling channels. As you can see on your screen, all the cooling channels has been implemented. This looks a little very weird, but this is possible with an additive technologies to include. So these were the some of the advancements happening into the injection molding. There are a lot of other advancement into the processing part of it. Because of the limited time frame, I cannot show you all, but yes, definitely in next some of the other times we will discuss around it. So with that, probably I will take a 30 seconds to summarize what we capture in today's sessions on that. We started with a basic, product design part of it. Product design, though it looks simple, try to avoid the chunkiness in your part, try to follow the best design guidelines on it. And I would say that designers or engineers are the key architect for it. How they design the parts gets replicated into the mold. We also touch base upon some of the best aspects into the cooling channels part of it, how simplistic cooling channels can be improved just following the guidelines on it. And of course, we also touch upon some of the new technologies are like the rapid heating and cooling and the AI into the cooling aspects of it. So with that, probably I like to hand over the presentations back to Mr. Francis. If any there are queries, I would be there. Please put your queries, questions into the chat box. I would be more than happy to answer.
Who is that?
Thank you.
Sachin, thank you very much for a wonderful presentation. You've kept the time perfectly. I don't know, can you unshare your screen? Yes, okay, thank you very much. Let's give a clap to Sachin, who's done very well to keep time. Fantastic technology, a lot of help for the designers, whether it's parts designers or mold designers. I think you've only touched on maybe half of what there is to say. So there's a lot more to say, but I think that will whet the appetite of our participants. I hope that they will go and explore more, through virtual simulation, prototyping, and so on. So thank you. The next speaker will be Miss Lim Wei Yan. She has a flight to catch after her presentation. So if you have any questions for Mr. Sachin, please hold on to it until the end. But for Miss Lim, after her presentation, she will answer all your questions. So if you have any questions during her presentation, please write it up in the chat box and she will address it to you. So over to you, Wei Yan, to talk about freeformers. Thank you.
Thank you, Eddie. Thank you for introduction as well. Yeah, so good afternoon, ladies and gentlemen. I'm sure you can see my slides and you can also hear me. So I'm Lim Wei Yan, Manager for Additive Manufacturing for Arbor, the freeformer. So today's topic I'm talking about will be 3D printing, prototyping, and small batch production using the freeformer. All right, so topics today, I will cover 4 topics. So basically about the Arbor plastic freeforming, the Arbor plastic preforming is using the DDM technology, so it's a dropless deposition modeling, and we will talk about materials and its properties, and sharing of some case studies, and last but not least, summary. Right. So when we talk about thinking additive, what does it bring us? As why is my slides doing automatic? Sorry. Sorry. Let me just cancel everything and redo this. Okay, so when we're thinking additive, right, as we know that typical product development is constantly changing. This includes rapid technical development, short product life cycles, the growing number of variants in each product, and customer-specific or personalized products. And all of the above requires a technology or process that can provide support in this regard. Additive manufacturing, known as 3D printing, which is an excellent solution here, and in our case, the freeformer. A familiar process for users in the AM flows this way. Firstly, a 3D CAD data in STL format is required. Secondly, the freeformer slicing software is used to orientate the STL data for material profile selections, auto generation of support structures, and slicing in desired layer thicknesses. This data is then transferred to the machine via LAN connection or USB thumb drive. Thirdly, the part will be built up layer by layer with droplets of melt material. Lastly, the finished part is completed. So this is basically a very typical 3D printing process. So let's look a little bit deeper into the Arbok freeformer. Here I will show you a video. And this video, let's say if the video is not playing well or is laggy, please always go to our official YouTube channel, or you can find a video there, or you can go to freeformer.com for all the videos and information. So as you can see in this video, there are two machine models, the 203X and the 303X. I'll go a little bit deeper later on. And this is an overview of how the software looks like. And this is what we use for data preparation. On the machine itself, the system is open. You can change the temperatures. As you can see, the material base we use is actually standard granulates from the injection molding. Inline drying is possible depending on material. So in this machine, it shows three different kind of nozzles. So now that you can see an injection screw in the machine, exactly like injection molding, picking up the material, melting it in three different temperature zones, dispensing it out in droplets format. So this is a 3-component product. It's a hard-soft combination with supports. And the build area is X234 and Y134 millimeters. After building, support structures are actually dissolved in water bath. So this water bath there's heat and there's movement for faster dissolve, like dissolving sugar. After dissolving the part, you can use it directly at the machine. In this case, we are putting it in the robotic arm from the injection molding machine. Here, following on, we're showing some examples like flip top covers or closures in PP, soft material, printing of one-layer scaffolds, soft material as well, and you are showing tear resistance here. The machine is biocompatible or clean room compatible as well. We can print implants or medical approved materials. So this is another scaffold, which is very elastic. You can see the pull. We're able to, of course, print lightweight structures, very stable spring kind of parts. A very special part here is actually a conductive material. Yeah. So moving on, as you can see, just let me quickly. All right, as you can see, this is where we use our standard granulates, exactly the same like injection molding. We put it into the machine, into the hopper. So coloring is possible via master batch, or when the granulate is already compounded with color, that's possible as well. So inline drying can be installed in our machine because most of the injection molding materials needs to be dried, right? So drying is required by the material, not by the machine. So as you can see also, material preparation via plasticizing screw, same like injection molding. Here you can see a very short overview of how the machine looks like interior. So hopper, screw, the hopper will be here, injection screw. We use a needle nozzle system for dispensing of droplets. Right. So let's go a little bit deeper into what kind of materials can we print. Because we talk about injection molded materials, we are talking about really a wide range of materials here. So With the use of injection molding based process and with dropless deposition technology, it allows us to cover a really wide range of plastic granulates or plastic pellets. So amorphous thermoplastics such as ABS, PC, PCABS, and amorphous PA are commonly used in the AM industry via extrusion-based technologies. This is possible with the free format as well, with additional option to print in unique blends like PA-ABS or PA66-ABS that is available from multiple material manufacturers. The material which is not common in the AM would be the semi-crystalline materials. Will be here. We will be the semi-crystalline materials, which covers, for example, PP and PE. However, we have successfully qualified and printed PP and PE, which is commonly used in the packaging industry for living hinges and snap fits. We also had success in printing different thermoplastic elastomers like TPU, TPEs, TPV, SEBS. So as you can see from all the videos and GIFs I have in this presentation, we are really very strong in printing flexible, as soft as going down to like 20 Shaw A. I'll go a little bit deeper later on. In medical, we have successful prints for implants which uses PLLA, PCU, PCL, and PMMA. These are materials used for long-term implants or resorbable implants in the body. Some companies in Europe has already sent this in for clinical tests. We're getting like some clinical test results pretty soon, probably early next year. So being said that, we are also able to print customized pills in the pharmaceutical industry using a glucose-based material. Special materials or customer-specific materials that is compounded with additive like carbon nanotubes. That is where in the video where I show you the flexible ribbon strip, right? That is actually a TPU compounded with carbon nanotubes that will create conductivity with it. So what we did is to actually embed the LED in, and that's where you see when we put on a power supply to it or just plug into any USB slot, this LED will light up. Basically, this function comes from the material itself. So due to a lot of complexity in designs right now, support structures is normally needed in 3D printing. So Ava has developed with different kind of support materials. We have two different kind of base, water soluble and alkaline soluble. And now we also have support material for PEI, which is breakable for high temperature, right? So when we talk about targeted adaptation of component properties here, we can actually vary the density of each component. So in this case, when you see this cube, it's actually polished on all sides to show high density and to show clarity. So we're not saying that we can print a lens here, but we're saying that we can really manipulate the droplets to create really high dense parts. Alternatively, when we talk about the TPE on the right, we have droplets spaced out much further to create a less dense parts, reducing fill levels. For example, normally a density is 100%, we reduce this to about 40%. So this creates and mimics the softness and feel of a sponge. And definitely we look further into varying densities, especially with the medical industry where cells needs to grow in. So varying of densities, increasing density, reducing the density is easily achievable actually with our software. So as mentioned previously, that one of the unique strengths of the freeformer is printing in soft materials. We have successfully printed shaw hardnesses as soft as 20 Shaw A to 95 Shaw A. And as we know, the softer the material, the difficulty of printing actually increases. So our softest is 20 Shaw A we have tried. So TPEs or TPUs, which are FDA certified with skin and blood compatible for FDA certified with contact to skin and blood is printable as well. Behavior of printed TPE and TPUs and TPEs has comparable properties to injection molding parts. And for multi-component parts like hand tool housing, a hard soft combination, where you see the hollow part where there is a need for support structures, we are able to print them all. Different kind of gripper system or spring elements for cycling and all these applications are really already done in our machines using the 303X machine here. So when we talk about future outlook of the freeformer, what do? We are now able to print actually Autumn 9085 PEI, which is very widely used in the air and space industry, and sometimes also in the electronics sector as well. We currently will have a new Autumn material, which is called 1010. The mod is by Sabic as well. Both materials are by Sabic, and they are FDA certified material to be autoclavable. So these are all we're able to process this on the freeformer. We recently launched this PEI material printing in Fakuma, which was just last month. So an overview of what models we have. We have two. So we have the 200-3X. So 200 actually means 200 square centimeters of built area. And for the 300 actually means 300 square centimeters of the built area. So typically the X is actually longer for the 303X. Right. So this model was actually 203X was launched actually in K Fair 2013, and we did a major launch for the Asia market and the US market in 2015. So since about 3 years ago, we have already launched the 303X, and it has been so far pretty successful in the automotive, medical, and electronics sector. So looking deeper into the 303X, so it has 3 nozzles, right? So the possibility of these 3 nozzles, it's multi-material printing in these options, right? In the case where supports is not used, you can actually use up to 3 different kind of materials in each print. That's provided if there's no supports. So when there is a support, we can do a hard-soft combination in the same build, or 2 different color with support structures in the same build. The third way to use this is actually, I can put in a hard or a soft. But these 2 materials does not mean that I need to use it in the same build. So it's just for convenience that when we do switching from material to material, we don't need to manually change it, but the material is already in the machine. So we do have Daimler Chrysler using the machine like 2 different kind of TPUs, like 150 Shaw A and 180 Shaw A, but they are not using these 2 TPU prints at the same time. They are just using it at different print jobs so that they don't need to change out material. So being said that, earlier on I mentioned that the build area of the machine is about 300 square centimeters. Build dimensions in X direction is 234 millimeters, 134 in X direction, and Y is 234. Z direction is 230 millimeters. So the basic machine highest melt temperature is 350 degrees. So in this 303X, we do have a high temperature option that we can arrive to a 450 degrees Celsius melt temperature for high temperature applications. So drying units connected individually to each individual hopper. So if I have 3 nozzles, I have 3 different dryers. If I have 2 nozzles, then I have 2 different dryers. That's how we deduce it. So I hope everybody understands probably the basic function of the freeformer. Now we'll go a little bit deeper into use case. So this is the latest case study from Germany. This company called Mosca. Mosca is actually an international manufacturer for packaging systems. So in each packaging systems, there are like 2,000 over individual components. And if one of them fails, the customer literally needs to replace it immediately. And many of the parts are difficult to reproduce using conventional methods. So the current solution, when a spare part, so this is more like a spare part replacement kind of example here. Reprogramming and repurposing the CNC systems, right, making them unavailable for other functions, because a lot of parts are very specific to the machine. So you need to change the CNC system to fit to the part itself. So Another way they use is actually outsourcing of these parts to other people for not printing, but for CNC. So normally it's very time consuming and the cost of production for low serial parts are pretty high. So Mosca is looking at 3D printing and of course to benefit the economic cost saving and all that. So what does the evaluation process for them means? So each printed part, right, needs to be verified with strength, dimensional stability, and speed. All right. So as you can see that this has met their requirements, and based on their calculations, the Arbor plastic free-forming process significantly reduces the cost of low production between 1 to 50 parts. So the cost is reduced by about 75%. And most of the components in the machine are either aluminum or plastic, such as POM or PE. And they are now currently printed in PA10, which is nylon 10, which actually, this nylon 10 is actually a better material to source and material manufacturers at a very low cost. So Mosca now prints overnight and ships the parts immediately instead of waiting weeks or months for components to be delivered. So based on their calculation, this is what they have tabulated. For example, a strap guide here. Conventional method would take about 14 days and each part is 36.77 euros. And using 3D printing with the freeformer, the time is about 80 minutes to print one, and the cost itself, right, is about $12.51. And when we're talking about cost per component is reduced by 75%. Right. Any other spare parts conventional method, right, will take about 14 days production plus 7 days shipping. So, but using the 3D printing with freeformer, we are doing it between 1 to 3 days production plus 7 days shipping. And the advantage that they see is actually economic production of over 100 low volume components, cost reduction through 3D printing on demand, lighter weight component structures and all that. Definitely reduce downtime and improve customer satisfaction because the delivery time to wait for a spare part is much faster right now. Enhance product development or experimental with new materials to improve their packaging machine as well. So this is Mosca. To have actually a more detailed read up on this, please get in contact with any with MPMA or with Arbor that we can send you this case study. Right. So the second case study.
You got 5 minutes, most.
Yes. I'm timing myself, don't worry. So the second case study here will be Summer Plus. Summer Plus is based on in Switzerland. This is more like a medical kind of example in small series production. So Summer Plus has been in healthcare since the 1960s. So the challenges is actually to put idea to market maturity. All right. It is crucial to put customers' needs front and center for them. So providing customers with a way to functionally test their parts and get to clinic trials faster is the main motive right here. So the ability to print medical approved implants such as Evonik Rhizoma or DMS Bionet. So the current solution and challenges, right? The parts printed conventionally, not printed, sorry. The parts produced conventionally is actually with injection molding, and they need to wait several months for appropriate mold. I think from Autodesk, you already know like having mold iterations is actually a very long process. So with actually 3D printing, they reduce this time by, I think, a long time, right? So additively produced parts, right, to have them being implanted to the body is not common in the normal 3D printing industry because they are not FDA approved. So for the freeformer, because we can use granulates, we can use directly the medical material that they need. So the wish for them is to actually get to different variations quickly and cost effectively, helping their client to get to the market faster. So these are some samples that they've printed in actually PCU. This is a Bionet. This is a long-term implant. And the resorbable implant, which is the Evonik at the bottom here, we are just showing you a difference between the IV. Because when we print, when we talk about IV, right, implant materials, we are more afraid of actually overheating. So this proves that actually the freeformer is suitable to use this material. So in summary here, traditional process of high volume production is 45 days, and then it takes about 28,800 francs. and production cost about 500 for 50 parts. So low volume about 10 days. But actually with the freeformer is 3 days and about 5 parts for 800 francs, which is with the time savings, they can actually balance out the cost here. So advantages here is 3 to 6 times faster time to market compared to injection molding, which is 6 to 12 months. All right, freedom of design so that they can customize implants for their patients, and also product development life cycle is reduced by 75%. So in summary, as you can see, that freeformer is an open system here, and we actually have a wide range of material possibility for customers to test the machine or for customers to use their own material in our machine. So Arbor being a machine manufacturer, we are constantly in development and improvement, which lets us present a large freeformer enables functional parts to be produced using up to 3 materials. Hence, we will call ourselves like a reliable partner. Right. So based on the 2 case studies, which are actual customer situations, we created huge success in obtaining fast and cost-effective solutions using the freeformer. So that comes to the end of my presentation. Sorry, Eddie, I probably overrun a little bit.
That's okay. We thank you for the wonderful presentation. I think it gives us a lot of possibilities. Right? My video is not on. How come I clicked it? Okay. So I think, there are lots of questions. So we will take up those questions now. The first question is, one of the problems of 3D printing, especially printing using thermoplastics, is VOC emissions. Is it any special design or solution to reduce the VOC emission?
I think the different kind of material selection can probably solve the problem here. Yeah. And definitely different designs as well, because us being open system, right? So we can have a really wide range of materials that we can use materials that has less emissions.
Sure. But I guess if you want to vent it out, you can vent it out through the roof and get a suction fan or something.
Yeah, I mean, there are like filtration systems that you can install, which are really small. With HEPA filter and all, you can actually use that as well. So when we talk about VOC emission, I think that is actually more for the powder printing or the liquid resin printing.
Okay, the second question, I hope I can understand it as well as you can. Can you integrate 3D printing with a preformed component by printing over the part which can be placed on the printing platform before printing starts? In other words, can you print over a preform?
Okay, I can print on any part, provided if the printing material actually has compatibility to the part that you want to print on. So if it's aluminium, most materials doesn't stick on aluminium. Probably you need to do like a coating over it before you can start to print. All right, this is one. We can print over a part, but it has to be flat surface, because why? The nozzles in our machine doesn't move. What moves is the platform. So if we have uneven surfaces, it actually will ram into the nozzle itself. So there are some considerations that we need to really look into it. But this example, exactly this example, we have it actually in the Lego store in Shanghai, that we have the freeformer there and they're printing like customization on their Lego brick itself.
Okay. That question then, hard soft components combination printing, is this machine, has it got a double nozzle, this machine? I think it has, right?
Yes. Normally hard soft component will need support structures. Then we need the third nozzle. So there's 3 nozzles. So they're printing not at the same time, but nozzle 1 will print first in the same layer, then nozzle 2 in the same layer, then nozzle 3 in the same layer.
Sure. Okay, the next question is about printing nylon 10 and polyethylene. Are there any effects on the quality or the properties of products when using PA10 instead of PE?
Definitely there will be some flexibility reduction there. So because the tensile modulus between these 2 materials is different. So PE is a little bit more kind of flexible, like very good for living hinge and all. But actually PA10 is not too bad. The cycle time is probably shorter just for PA10. So tests have to be done.
Yep.
to see how you want to replace it.
By the same token, this is a much stronger material, yeah?
Exactly.
Okay, another question is, this is a good one. What's the pricing of these 3D printers?
I think better get in contact with Albert. We have 170 people here.
Okay. Kids, if this is by kids, actually, kids, if you want a special price, go and bring them up and have a meeting.
Yeah.
Okay. So the question 6 is, Ms. Lim, does the freeformer generate supports automatically of the supports also needed to be designed offline with intended 3D parts?
It's generated automatically by our freeformer software.
That's good. That's a short one. Okay. How do we get in touch with you to arrange a demo for some follow-up questions or at a later date?
I think
Can we give a demo?
Oh, we can, but you know, with COVID, it can be a little bit stringent here. So, I mean, if you can travel to Singapore, we welcome you. We have a demo machine here. You can come anytime. I can arrange a demo even like online, maybe via Zoom. It's possible. Just get in contact with us. If you don't have our contact, get in touch with MPMA. MPMA has all our contacts.
Any chance of getting one machine up to KL so that we can all, flock to KL and see a demo and buy a machine, perhaps?
We actually had plans to have like a seminar in like Penang, but because of COVID, right, everything got delayed. So let's wait till the borders open and see what happens. We will definitely plan something.
Yeah, I'm hoping that you get a machine up to KL, so you can all, play with it or do the demo and so on. Okay, wow, many more questions. How may we get in touch with you? I think get in touch with MPMA. I think that question is answered. Contact MPMA, whoever asked the question. Ron from KLK Oleo, 3D printing technology uses DDM method. I don't understand that. How is processing aids being added into for functions such as slip additives, rheology, and etc. for different polymer palettes? Can you add
okay,
modifiers?
DDM actually means droplets deposition modeling, and only the Arbor freeformer has this technology. Nobody else has it because it's patented.
Yes.
All right. So, of course, when you're talking about processing aids being added for functions like slip additives and all that, right? We don't compound the material, so you really need to get in touch with a material manufacturer to get that done.
Okay.
And then we will test the material for you to be printable or not.
The next question is budgetary cost of both models and standard materials choices. So I think get in touch with Albert again.
Yeah. Yes.
Question 10, how small are the droplets formed during the layering step? And if I may ask, how fine can the finish be, in terms of CLA or whatever?
In Z direction, our minimum is 0.2 millimeters. In XY direction is 0.6 millimeters. So basically one droplet is 0.2 millimeters.
Oh, okay. That's good. So that gives you some idea of how fine
this
is. Next question. He should be able to provide price range to avoid unnecessary inquiries. So up to you, Wayan, you want to ask that?
I think Suzata already posted my email in the chat. So please take down my email. If you have any questions, just drop me a mail. I'll try to reply as soon as possible.
Yeah.
All right.
I think that's about all the questions we have for you, Wayan. So thank you very much for a very insightful sharing. And I really hope that you can get a machine up to KL, because you see from all the questions, there are many people interested, but going down to Singapore can be a little bit tricky.
Yeah, let's talk to David.
So David, David Chan, the same David Chan.
Yeah.
Oh, okay, my old friend. All right, send my regards to him when you see him, man. So thank you very much. Have a safe
Thank you, and thank you, Eddie, for accommodating to my time. Thank you very much.
Thank you very much. Have a safe Germany. Okay.
Thank you.
Let's move on to the next speaker. Sato-san, are you? Oops. Sato-san, are you ready? Yes, you are. So
yes,
talk to us about these special engineering, high-tech materials. Thank you.
Okay, thank you very much, Eddie, for the introduction. And I'm Yasunobu Sato, APAC Transportation Marketing Manager at Solvay Specialty Polymers. So it's my honor to kind of introduce our specialty polymers to you, and I hope it will be helpful for everyone in the future for choosing Solvay specialty polymers products. So today I would like to kind of go through a very short introduction of our company first, and want to introduce what we're doing a little bit around sustainability. And after that, I will deep dive into the products which I would like to introduce to you today. And also with the recent applications of the products which I have written here. Products will be around polyamides, polyketones, sulfones, and liquid crystal polymers, and some fluorinated elastomers. And I will end it up with a short summary so that you can take back my key points for today. So let's go into Solvay's history first. So Solvay is a Belgian chemical company. It was founded by Ernest Solvay about 158 years ago. So it's a company with a long history, and maybe a lot of you know Solvay because it's the method of producing soda ash. So it was founded a very long time ago, but I would like to focus here today is that we are very good at innovation. As you can see in the lower picture, we are having, we still have these Solvay physics congresses every 4 years. And as you can see, at that time, Dr. Einstein and Dr. Curie has attended these congresses. And we kind of want to, use fundamental science and innovate applications for the future. So Solvay really cares about innovation. And you can see some of the applications such as plastic bottles, which were invented by Solvay, putting in silica into green tires. This was also invented by Solvay. So Solvay is really, interested in innovation. What is Solvay today? We are a science company. Today I will be introducing you engineering plastics, but since we are a chemical company, we do a lot of things. We still continue to produce soda ash. Also, we do a lot about surfactants. Also, we actually sell vanilla, which is made, which you can put into your chocolates. So, but today I'm from the global business unit called Specialty Polymers on the left-hand side, which is our material segment. And I will be focusing on our engineering plastics, which we call Specialty Polymers. We are currently under, a sustainability plan. We call it the Solvay One Planet, and there are 3 major approaches which we are taking to conduct this sustainability project. So first, what we are currently doing in sustainability is with our customers, we are developing lightweight and electrified applications with our product portfolio, and that's mainly connected with the e-mobility applications such as battery electrical vehicles. Other than that, we are trying to reduce our carbon footprint in our manufacturing. So we are using renewable energy at the most. So for example, in North America, our products are manufactured 100% with renewable energy. And from a product development side, we are using bio-based raw materials, recycled materials, and that's kind of ongoing right now. So I mentioned about e-mobility systems. We are focusing on e-motors, e-drives, power electronics, and batteries, and hydrogen. So these are 4 big areas which we would like to support with our product. And there are a lot of strategic initiatives for each of these areas. But at the end, it's all about how we can, make vehicles efficient enough by also with safety and lightweighting and performance. And our product portfolio can support this. So that's kind of the story which I would like to tell you about today. Now, before going into our product portfolio, I would like to show you what we have as a big portfolio. As you can see, this is a pyramid which we call the plastic pyramid. There's a gray part and also the blue part. And what we handle, actually, what we actually manufacture and sell to our customers is something in the blue part. And the blue part is, the top of all of the plastics. So we call this specialty polymers. And as you can see, the white bold abbreviations of plastics, those are all the plastics which we actually manufacture by ourselves and sell to our customers. You can see that on there, the pyramid is divided into 3 sectors. The left-hand side is amorphous. So in the amorphous sector, you can see polysulfone, polyamide, imide polymers in that area. In the middle, you can see the semi-crystalline sector. We have a lot of semi-crystalline materials, majorly talking from the king of super engineering plastics. It's polyether ether ketone, but also we handle PPA such as aromatic polyamides. And on the right-hand side, this is not plastic, but we also are strong in the area of fluorochemistry. So we handle elastomers, such as fluoroelastomers, which is mainly used in O-rings and gaskets of internal combustion engines, but very good in high temperature and high chemical resistance. We also handle fluids, which is a kind of a short polymer, fluoropolymer. It becomes an oil. So maybe some of you have heard about fluoro grease, which is added in some of the applications. The fluid is something that we provide. So we are a global leader in aromatic and fluoro specialty polymers. And today I will be choosing some of the products which we have, and I will introduce you the newest applications, which is where it is used. Just to mention how good our engineering plastics can be shown in this graph. The x-axis is the glass transition temperature, and the y-axis is the heat deflection temperature. I kind of put in PA66 and PA6, which are the general, I think, plastics which are commonly used a lot. The blue kind of dots and the open blue dots are the products which we have. So as you can see, what we have in our portfolio is higher in glass transition temperature and higher in heat deflection temperature. So in that sense, we have a portfolio of high mechanical strength at high temperatures. So that's what I wanted to rephrase here. And that can be said also with the amorphous type of plastics, which is on the right-hand side. Amorphous plastics only have a glass transition temperature. And I think polycarbonate is, I think, a commonly used plastic in that area. But what we have is, better than polycarbonate. So higher glass transition temperature with a high deflection temperature. So what you cannot do, or if you have difficulties with normal nylon PA66 or PA6 products, then Solvay is the company to ask for support. Also with the polycarbonates, if you have trouble with polycarbonates, then Solvay is the company you can come and ask for support, and we can provide you the answers and solutions for your applications. So that being said, today I have selected some products in our portfolio, which shows there's a lot. I think Solvay is the only company who has this broad, wide range product portfolio in the area of engineering plastics. And I can definitely show you some of the way to use these products in the areas where, such as e-mobility or battery electrical vehicles will be, the trend for the future. So let me go into the first area, which is aromatic polyamides. So polyamides normally PA6 and PA66, those do not have an aromatic group. So what we have in our product portfolio is a polyamide which has aromatic groups. Amodel is one of the major brand names which we use, which is a polyphthalamide. There are other aromatic polyamides such as XF and Calyx, but today I will focus on Amodel. Now, when you need to use these PPA, polyphthaleamides, is when standard nylon does not work. Advantages with these polyamides are thermal performance and, of course, chemical resistance and stiffness and surface appearance. Absorption of water is very low due to the aromatic group, and aromatic polyamides also show very good electrical properties. So key applications are under the hood applications in automotive, but currently we see a lot of inquiries in electronical applications because automotive sector is becoming electrical now. So several applications which I have written there are terminals and sensors which are focusing, and we have a lot of customers in this area right now. One key point for using Amodel, we have a lot of grades within Amodel, but what I would like to stress today is a relevantly new grade, which is called Amodel AE. AE actually stands for Amodel Electrical, so it is for electrical applications. Now, in the past, when you use polyamide material, normally an inorganic heat stabilizer is used. Now, these inorganic stabilizers can corrode the surface of metal, so that's not good. So what we have been developing and what we have launched in the market is a Amodel PPA, which has organic heat stabilizers. Now, if you use this, it will not corrode the metal surface. So, for example, in bus bars and sensors, normally there are metal rods coming out of the plastic over molding. So we would like to propose you to use Amodel AE grade. And we have a lot of, in a broad range of AE grades, but currently the 35% glass-filled Amodel AE is becoming a trend due to the trend of e-mobility and also applications in battery electrical vehicles. So this is one of the key points which I would like to stress here for polyphthalamide. Next, I will go into polyketones. Now, polyketones, you might have heard about PEEK, polyether ether ketone. Now, this is the best of the best. I mean, if PEEK does not work, normally, everything will not work in plastics. So, best combination of fatigue resistance, chemical resistance, and mechanical properties at high temperatures, and it's kind of the king of plastics. King of plastics. It also shows excellent electrical insulation properties. So I'm going to show you one of the applications of that. And there's a lot of customized grades in this area. And we have a lot of flexibility in developing new formulations in this area. A lot of applications are around aerospace, but currently we see PEEK used in a lot of automotive components for electrical insulation and liquid sealing properties. Other than that, it is used in medical devices, of course, and oil and gas components. So in the e-mobility sector, how is PEEK used? Now, this is actually not an injection molding application, but I think it will be interesting for you because I think this is one of the future applications where we are seeing right now. Now, it's using electrical insulation of the Kita spire PEEK, and it's extrusion of wire, so extrusion of wire coating. Due to the good dielectric constant, in other words, the low dielectric constant of PEEK and the high temperature resistance of PEEK, and also the good elongation of PEEK. Currently, the high-end motors are using these magnet wires coated with Kitaspire PEEK. So PEEK is extruded on top of these copper wires, and they are winded into the motor slot, which you can see on the right-hand side. So our Kitaspire PEEK is used in this area, also showing good, excellent quality for extrusion process. And for instance, for our customer, they are manufacturing a square type, rectangular type of magnet wires instead of the round type magnet wires, which will improve the efficiency of the motor itself. Now, as you can see, it is PEEK is a material which can be used for electrical installation in extreme conditions. And I believe that in the future, there will be also a lot of injection molded applications for e-mobility coming up. So please keep an eye on that. Next, I will be introducing sulfone polymers. Now, sulfone polymers are amorphous polymers. So they only have a glass transition temperature. Now, here I'm showing PPSU, polyphenylene sulfide, polyphenylene sulfone, polysulfone, and polyether sulfone. And they are normally used when polycarbonate is not good enough. Performance is okay, it's transparent, and thermal performance and chemical resistance are also, superb with these polymers. Normally they are used in plumbing, aircraft, interior trolleys, and those kind of applications. But today I'm going to show you an application in transportation, e-mobility. Now it's used for fuse blades. So it's the fuse for e-mobility. And due to this high volume resistivity, which is an electrical property, and the transparency of the material of sulfone polymers, you can color this material and you can separate the fuse, which has different resistance to different amperes, electric currents. And these kind of fuses will be kind of put into the fuse box at the end, and they will be, the color coding will be used for identification. So we are seeing heat resistance. We are seeing some increase in heat as the voltage of our battery electrical vehicles are, getting higher and higher. We are also seeing higher electric current, which means that thermal resistance is needed. So we are seeing some increase in sulfone polymers in fuses. And that's also one of the trends of e-mobility, which is coming up right now. Next, I will be showing the liquid crystal polymers. Now, this is a kind of a unique polymer. It's a crystalline polymer, but it shows very high flow, meaning that you can easily mold into intricate thin-walled parts. So on the right-hand side, there are some photos of the terminals, very small terminals with a lot of small metal electrodes coming out. So it can be molded in those kind of shapes. And due to the inherently flame retardancy of LCP, liquid crystal polymers, it can be used in a lot of areas. So mainly in the past, it was about connectors, SMT components in the electrical market. But what I would like to show you today is something quite new. Now, our customer has been using a 30% glass-filled liquid crystal polymer, LCP, Zyda, and it is used for slot liners. Its slot liners, a very thin kind of paper-like slot liner is injection molded, and it's actually put into the motor. So this high flow material LCP can be used, and it does not, since it can be injection molded, you don't need to machine out the final structure, which reduces the cost at the end. And LCP has a excellent electrical insulation, so it's also good for slot liners in motor systems. And the slot liner is, of course, for electrical insulation, because the rotor itself is mainly metal, and you need to insulate it from the magnet wire. And that's why these slot liners are used to secure the insulation. And this is a relatively new application with liquid crystal polymers, and it was awarded just a month ago in Europe at the SPE association. And I think these kind of applications will also increase in the future. So finally, I will go into two applications, not related to injection molding, but I think it will be interesting for you. Fluorinated elastomers. Technoflon is a brand name. It's an FKM. And our FKM, fluorinated elastomers, it's a rubber, are used currently in a lot of O-rings and seals and gaskets in automotive and aerospace area. Reason why I'm highlighting this is due to the increase of the rotation speed of the motors in the future. You need a better sealing for these rotating parts. And what we actually have is a peroxide curable FKM. And this is better in chemical resistance and also temperature resistance. And for the future, we will definitely see an increase in these sealings with FKM Technoflon. So that's a kind of new area which is coming up. And at the end, I'm going to show you an area where we are putting in effort, which is polymer films. Now, what I have introduced was, mainly about plastics or, specialty polymers, which are in pellet form. Solvay is actually capable of extruding films right now. And what we are currently doing is we are manufacturing films in a broad range of high performance polymers, because we have a broad range of specialty polymers. We can control thickness of these polymers, these films, from 6 microns to about 1.5 millimeter. And we can extrude it, the width is about 1.5 meters. So there are some photos of our facility in North America, and we are trying to propose our customers these new type of specialty polymer films, which is very important in electrical insulation. So we can actually make pellets. I mean, we can compound things. We can actually make base resins by ourselves. And we are now also extruding these things and making films for our customers. And one application is electrical insulation films, such as slot liners. And we can actually do a formulation by ourselves. So we can actually tweak the thermal conductivity and all those things, which is a request or inquiry from our customers. So the final page is about e-mobility. We have a brand new e-mobility website. So if you are interested in e-mobility, please come to our website. It will be showing applications around e-motors, e-drives, and power electronics. And we will show you how our Solvay product can be used in this area. And as a summary, I would like to summarize today's presentation. And I introduced you a lot of products which we actually manufacture by ourselves. It was mainly about aromatic and fluoro specialty polymers. Since I'm from the transportation sector, I have kind of focused on e-mobility applications. But one important thing here is that electrical insulation is going to be a key property in plastics for the future. So keep an eye on that. And what we can give you and what we can do is that Solvay has solutions to this. When you have issues with electrical insulation, with plastics, please contact us or contact my direct email and send me an email so that we can support you in a lot of ways, because we have the broadest portfolio, wide portfolio in specialty polymers. So that's all. Thank you very much.
Thank you very much. Am I on? Yes, I'm on. Sato-san, thank you very much for a wonderful presentation. You've given us a lot of new ideas, I guess, what is possible with some of these super duper engineering plastics. A lot of good properties there. So participants, you are now allowed to ask all sorts of questions to the first speaker and to the last speaker, to Sachin-san and also to Sato-san. So
Mr.
if wants to start firing, yeah.
Mr. Eddie Fong, before we do the Q&A,
yeah,
can we do the poll first, Mr. Eddie Fong?
Oh, you want to do a poll? Sorry.
Yeah, let me do the poll first, then we can carry on with the Q&A session.
Okay,
Ladies and gentlemen, before we have the Q&A session, we would like to do a quick poll to assess the webinar. This is to help the Secretariat understand the areas of improvement for future webinars. Kindly participate by giving us your answers. We will just hold this for 1 minute. Can we have the poll on? Yes. Okay, come. We'll just do this for 1 minute. Then we'll move on with the Q&A. Can everybody please give us your feedback on the 8 questions that you see on the screen? You just have to press the replies. Okay, we got 1. Thank you so much. So far we have 1.
We should have about 140 or so replies, because we got 165 people left here.
Yeah, we've got up to 8 so far. Come, that's good. That's good.
We peaked at, I think the numbers peaked at about 183 just now. I saw. So it was a good session. Thank you all for joining us. Yeah, this the poll will help us to understand you better. Then in future, what we need to do to improve our webinars and so on, and how we can reach you, market it to you, etc.
Okay, we've got about 49 replies so far.
Very good, very good.
Okay, we're up to 53. Very good. Can we have more?
It only takes about 2 minutes, so let's hit 100 then, huh?
That'll be nice. Can we get to about 100? We got 62. Thank you. We're up to 68. Very good. Thank you. 69. Can we have a few more? Come on.
I cannot vote, Francis.
It's not for panelists.
I know.
It's only for participants.
Just pulling your leg. How many do we have now?
We have already 79.
Okay.
80.
Can we hit 100? 79 and going.
We got 82.
Okay. Let's give it another 2 minutes. We got time. It's only 4:15, so it's going to be an early break if we finish in 20 minutes. So
I think, Mr. Eddie Fong, we should stop here. I think it's okay. Let's move on to the Q&A session. Thank you so much, everybody. Come, Mr. Eddie Fong, let's do the Q&A.
Let's go to the Q&A. Sorry, my phone takes some time to turn on webinar. There are not many questions that I know I have started. Okay, so participants can start posting, please. All your questions. I think we'll start with Sato-san. Sato-san,
yeah.
Somebody asked the question. These engineering plastics are very hard to machine, very abrasive, very hard. Can you give us some guide as to how to machine these engineering plastics like PESU, PEK, PPSU, and so on?
Okay. I think that's an important question. Of course, you will need injection molding machines which can handle at high temperature. Of course, you will need that. Now, is it too abrasive?
No. Sorry, he's talking about machining, as in cutting and milling and.
I see. All right. Sorry about that.
Sorry.
Actually, there are kind of blocks of these plastics which you can buy, and you can machine it out without, not big issues. I mean, machining out is not a big issue because, for example, for peak, normally a lot of customers machine out and make initial samples. But when you need to manufacture a lot of parts, then you shift to injection molding.
I guess if you have glass, 30% glass filled material, then the cutters will wear out a little bit faster. You might have to use carbide or diamond cutters, I suppose. Yeah.
Yeah, that's of course absolutely. Yeah.
So following that question, you mentioned about the equipment. Now these are very high melting point polymers. What sort of equipment can we use? A conventional injection machine, or do we have to have special equipment, screw barrels, heaters, Tell us more about how to process these materials.
Okay. The details of these, I mean, injection molding machines, I think it would be better to ask the details to our customer technical service because they are the professionals in the area of selecting machines. But one thing that I can mention is that it needs a high heat. I mean, you need an injection molding machine which can go up to 300, 400 degrees Celsius, of course. So that's something that you need. And also on the mold side, depending on the plastic you use, you might need better metal used for the molds. So, but for the details, please ask our survey key account managers or customer technical service who can advise you on what kind of machine will suit your application or molding.
So in other words, go to the website and find them, yeah? Yeah,
of course. And you can also contact me and I can appoint a person who will be able to answer your questions.
Sujata, are you posting, Francis, are you posting the contact email for Sato-san?
Yes, I just did. It's in the chat box.
Okay.
Yeah, there are some more questions in the WhatsApp group.
I know. Okay, let's go to Sachin. Sachin, questions for you. Regarding cooling channel design for a fan, you have shown earlier, it looks very interesting. May I please ask how many axes does it require to design a cooling channel that way?
Sachin? Indeed, I was also excited to see those complex cooling channel. These are again, these are artificially designed by the computer. So we use a AI technology, a generative design technology from Autodesk. At this point of time, it is at the concept designs or concept level or at the consulting stage. It's not commercially available at this point of time. Answering to your question, how many axes does it need? Probably it needs like in 5 axes actually. If you see, those are complex and cannot be manufactured with a traditional milling. Even if you have like in 7-axis machine as well, it's quite a complex. So I would prefer to go with the metal 3D printer inserts, particularly for those channels, and then I can use a traditional block to fit in those additive manufacturer inserts in that. So that way I can achieve it more effectively or efficiently. Okay. I hope that answers your question.
I hope so too. Somebody asked, Mr. Chi Hok Wong, mold temperature too high. We don't understand the context of the question. Maybe you want to rephrase that again and ask. Sachin, I got another question for you. You talk about mold flow. I was a guinea pig of mold flow something like 43 years ago. Now, mold flow is quite expensive to buy the whole package. Is there a way we can like pay as we use for mold flow, like a rental basis?
Absolutely, and Autodesk is hearing the voice of the customers on this. So if you want to buy a glimpse of mold flow or to just get an access to it, probably we have a beta version of mold flow getting into the Fusion 360. And Fusion 360 is a online, I would say, on the cloud, CAD modeling, I would say CAD modeling plus manufacturing. And recently we added an injection molding technology in it. Yeah. It's available at the no cost at this point of time. It's a preview. So if you really want to, get a gist of the mold flow, what mold flow is all about, I would say that easiest way is download the Fusion 360. It's available 30 days trial over it. And if you want to buy, it's much the easiest way to get the hands-on on the mold flow. I cannot disclose the price, but I would say the easiest way, and even an individual can buy a Fusion 360 and gets a hands-on onto the mold flow within the injection molding technology within the Fusion.
Thank you. Sato-san, the question here is, PEK needs more than 300 degrees to mold, in the injection molding machine. What about the mold temperature? Does it need a very high mold temperature too?
Yes, I think I can give you a tip on how to select the mold temperature. Now, as I think a lot of you know, plastics, especially for semi-crystalline plastics, these plastics have glass transition temperature. Now, you normally need a higher temperature, higher mold temperature than the glass transition temperature, okay? So, for example, with PPS, thank you there, I think 2 questions on mold temperature from Muniandi-san and Wong-san. So, for example, with PPS, PPS has a glass transition temperature of 90 degrees. That means that you will need a mold temperature higher than that, at least 90 degrees. But normally, my understanding with the PPS is, I think they use 120 or 130 to be on the safe side. Now for PEEK, polyether ether keton, okay, has a very high glass transition temperature. It actually has 150 degrees per Celsius, which means that you will need maybe more than that. And normally, what I use when I do my self molding, I use about 180 degrees, 180 as a mold temperature. So you will need that setting, type of setting when you use PPS, use PEEK for that. So that's why I said that, the machine or the injection molding machine and the setup you use need a high temperature resistance or high temperature profiles, which we can use for injection molding. But I think overall, the most important thing is try to check the glass transition temperature of the plastic which you use, and normally add 20 or 30 degrees on top of that for a mold temperature, which is, I think, a general rule of thumb when you do molding. Eddie, you're on mute.
I am, because it's very noisy in the background. It's just a storm outside. Yeah, thank you for the answer. I think that's a good guideline. 20 degrees above the glass transition temperature for your mold temp. That's to help to crystallize it a bit. Okay, more questions. I think the same one. Oh, for machining of these polymers, the engineering polymers, Sato-san, do you suggest dry or wet machining?
I think my understanding is normally they are done at a dry state. But if it's a kind of a question on a detailed, maybe a specific condition, please contact me what you are trying to do, because then I can appoint the right person who can answer you in a good way.
Okay, thank you for that. Yeah, I think you need to look at the specific application maybe a bit more. Okay, question here to also Sato-san. Will the prices of super performing plastics coming down to the level of metals in future? I'm not sure how you want to answer that. Will the price of super performance plastic come down to the level of metals in future?
It's that's I think very difficult to answer. Yes. I do not know how metal price will change. I actually know that the metal price is increasing right now. So, but in general, it will not be exactly the same as metal. I mean, from a general point of view, normally there is value when you use super engineering plastic in metal. For example, lightweighting, but not just lightweighting. You can also combine for example, things which cannot be done with metal. So you needed to understand the value and also make the value as much as possible when you introduce these things. And that's what I think is the good part of using super engineering plastics. Yeah. And we can actually show you what the value is. Actually, today I showed you the e-mobility website which we made. We are kind of showing the value of using engineering plastic, even though it's costly compared to metal. But combining features of what was done in the past with metal, you can do it in maybe one shot. So those kind of value is something that you will need to understand. And please contact us. We can provide you information on in what way you can create value with our super engineering plastics.
And also not to take away is that metals are usually 8 to 10 times more higher density than engineering plastics, isn't it so? So 1 kilo of metal will get you very little volume. 1 kilo of engineering plastic will give you 8 to 10 times more volume. So in that sense,
correct.
It is quite economical in terms of cost effectiveness. Yeah. The
correct.
other question is can these super engineering plastics replace steels now?
Actually, from the
replacement,
actually from the point of the mechanical properties. From a mechanical point of view, for example, polyether ether ketone PEEK is used a lot for metal replacement. Today I didn't introduce you, but we have a material called polyamide imide. This actually performs, almost the same as metal.
Is that PAI, polyamide?
Yes, polyamide. Sorry, but maybe my pronunciation was
sorry.
It's PAI. PAI actually Solvay actually has. Well, we are the only manufacturer who can provide injection moldable PAI. PAI normally, I think, is used, by dissolving it into organic solvents and maybe for coating. But we can provide injection moldable PAI. And for these materials, it's almost the same as steel. So depending on the application, you can actually replace metal. Now, an area where we see a lot of metal replacement is in gears. So if you are interested in gears, you will see a lot of metal replacement which is coming up.
Okay, thank you very much. Are there any more questions in the screen? No, I don't.
There are none.
I don't see any more.
Yeah, there are no more questions.
So, all right. I think thank you very much for the speakers for answering those questions, giving us very interesting talk. I think it's opened up our view of what else is possible with these higher engineering plastics. Sato-san, one last question from me. In Malaysia, how much of these super engineering plastics do we use in terms of tonnage? If you lump them all together, would that be 5,000 tons, 500 tons, 1 ton or 10 tons? Would you have any idea at all?
In Malaysia, you mean?
Yes, just specifically Malaysia.
I actually don't have a value for that, but I assume it's not that high at the moment. But as you can see, I'm from Japan right now. I know a lot of Japanese molders are also there in Malaysia, and they are molding with these super engineering plastics. So I'm quite sure, as for example, in the automotive industry, they are shifting production, into Southeast Asia. Then I think you will have a lot of chances or opportunities using these super engineering plastics. But sorry, I don't have the number for today.
That's okay. I feel that maybe in Malaysia we could explore these engineering plastics a lot more because we have basic infrastructure of injection molding, and we just need to get more sophisticated equipment, better heaters, ceramic heaters, and maybe better screw and barrel materials, to just transit into higher value added, no doubt. Huh?
Yeah,
so
absolutely.
Yeah, thank you very much. Okay, I think that's all from me. Thank you very much to the speakers for the most enlightening talk and answering all those difficult questions. Francis, over to you.
Thank you, Mr. Eddie Fong. Before we end today's session, I would like to request for the panelists. Okay, Mr. Sachin, you got your camera on. Dr. Sato, Mr. Eddie Fong, Secretariat staff, are you going to put on your camera? Sujata, come. Yeah. Mr. Chan, are you there? You want to put on your camera?
And while you're speaking, I saw that there are some guests. Dr. Velu is with us. Actually, he's not showing his face. He's a guest with us. And I think Aini from Ben Mayer is with us, with Nicholas. They are with Dr. Sato.
I think, can we proceed with the photograph? Wendy, you don't mind? Wendy, come, let's smile for the camera.
Everybody look at the camera, don't look at the screen.
Okay, okay.
I don't know, is it?
Wendy, okay.
Yeah, I've taken it. Okay.
Okay, thank you. Mr. Eddie Fong, you want to close the session, Mr. Eddie Fong?
Yes, I think the session is very informative for those of us who aspire to go into these higher value products. First of all, you can design better. You can do a lot more testing while it is on the drawing stage, so to speak. Although we don't draw on paper anymore, but it's drawing on a CAD program, designing through Autodesk, and then verifying your product through mold flow to see whether the flow is correct and the gates are in the right places, the weld lines are strong enough, and so on. So mold flow is very, very useful, especially if you're doing a lot of design of products and do your own injection molding. Then you can go and buy an arbor machine and do your 3D printing to verify your design, to see whether it feels right in your hand, to see whether the curvatures are correct and so on. Because not everybody can imagine in 3D so well. Some people, your managing director, who is probably not practical or not technical, I should say, might not feel, what is the R2 radius feel like, So unless you can give it to him in his hand, then he does not know how to feel. So, do a 3D printing model and so on. And then with the 3D printing, with Autodesk and the 3D printing, the free former doesn't print in metal, but you can get 3D printing machines that print in metal. So you can make your inserts with this conformal cooling, like Sachin is saying. And you can get optimum cooling. You've seen examples of how you can reduce the cycle time by 67%, just doing conformal cooling. So if you look out, if you work out the cost saving over, say, 1 million pieces, it's well worth your while to do the 3D printed metal insert. In fact, it might be worth your while to buy a 3D metal printing machine to make inserts, if you're into that kind of high volume products and you've got many machines and many molds to make. So and going on to the engineering plastics, I think there are lots of metal replacement applications that we can think of, especially now with weight saving possibilities. You also talk about sustainability. People are talking about saving fuels and so on. Although fossil fuel they think that fossil fuel will be outdated eventually. But in the meantime, we can save a lot of fossil fuel by lightweight engines, lightweight car components, by using some of these engineering plastics instead of metals. So, the kind of your imagination is your limit, really. So if you can synergize all these things, knowing your materials, knowing how to design them, knowing how to design the molds, knowing how to process them, use the right ancillary equipment, the dryers and so on, using the robotics to automate some of your process. I think the plastics manufacturing industry has a bright future, not only for the world, but for Malaysians. But the secret is that we dare to try and innovate. So with that, I shall leave you, and hopefully you can go back tonight. I hope you can lose some sleep thinking about what is being said and try to, bring productivity gains to your operation, bring more profits eventually, and also make it sustainable for your company. Thank you.
Thank you, Mr. Eddie Fong. Once again, a big thank you to our panelists, Mr. Sachin and Dr. Sato, and Wei Yen, who has already left, and to our participants for staying with us to the end. Have a pleasant evening and stay safe. Thank you.
Thank you.
Thank you.
Bye-bye. Thank you. Bye-bye. Thank you.